Welcome to assignment 82, our last new material for the semester, and this is all about evaluating integrals. Now, so this is the way we can evaluate an integral with what we know right now. And that method is going to be by appealing to the geometry of the situation. And what do I mean by that? Well, let's take a look. If I have the integral from 0 to 2 of x dx, that's the same as the graph of y equals x from 0 to 2. And since this is the graph y equals x, we know this ordered pair is I plug in a 2, y equals 2, so 2, 2. So what I'm looking at then, if I'm saying, hey, what's the area under the curve from 0 to 2 on this function, I'm saying, what's this area? Well, that's just the area of the triangle, whose base is 2 minus 0, or 2, and whose height, the y value here, is also 2. So this is going to be 1/2 base times height, or 2. See, I can evaluate an integral because I know that integral represents the area under the curve. With that being said, knowing that we're supposed to be appealing to the geometry of the situation, I think you should be pretty comfortable evaluating these integrals. So how about this one? 70 from 3 to 5. Okay, give it a try. And yeah, of course, you could certainly do the constant times b minus a, which in our problem is 70 times 5 minus 3, or 140. But we want to appeal to the geometry of the situation because that's what we were told to do in the directions. So let's see what that could be. Here's 70, and there's 3, the lower boundary 5, the upper boundary, and we're looking for the value of the integral. This is 70, and this is 2, 5 minus 3. So 70 times 2, same 140. Nice. How about this one? The integral from 2 to 4 of x dx. Okay, so did you think about this as a trapezoid? I know I've got that line y equals x, but I'm only going from 2 to 4. And so what I see there is not a triangle, but a trapezoid. Now, remember, the formula for area is 1/2 height base 1 plus base 2. This is the height here, so that's going to be 4 minus 2. Base 1. Well, base 1 is what the y value when I plug a 2 into the function. So 2 and base 2, this length, is what y value I get when I plug a 4 into the function. So I end up with 6. 6 is the value of this integral. 6 times 2 times 1/2, which is 12 divided by 2, or 6. How about this one? How about the integral from -2 to 2, square root 4 minus x squared dx? Yep. You know what that is, or you're really supposed to know what that is. How else can you appeal to the geometry of the situation? So, for those of you who didn't recognize it, this is a semicircle. It's only the top part of the circle because we only have the plus. We have the minus, it would be the bottom part. And we're looking for the area between the curve and the x-axis. Well, that's half a circle. And we know the formula for area of a circle is pi r squared. So area of half a circle is going to be pi over 2 r squared, or pi r squared divided by 2. In our situation, r equals 2. There's our center, there's our radius. So I'm going to have pi over 2 times 2 squared, or 2 pi. The value of this integral is 2 pi. How about this one? The integral from 0 to 2, absolute x minus 1 dx. It sure does help that we have powerful graphing skills so that we understand what we're looking at here is simply the absolute value graph shifted 1 to the right. And we want to integrate from 0 to 2. So there's 2. We don't need that. We don't need that. Oh, 2 triangles. There's 1. Well, how high is this? If I plug a 0 in here, 0 minus 1 is negative 1. Absolute value of negative 1 is 1. If I plug a 2 into this, 2 minus 1 is 1. Absolute value of 1 is 1. So I could do 1/2 base times height plus 1/2 base times height. Or I could say, well, I think there's symmetry going on here. I've got 2 times 1/2 base times height. And so those will cancel, and I'll get an area of 1. The value of this integral is 1. What if we change that? What if we change that boundary to be 3? Can you do that one? Give that a try. Come back when you're done. Hey, welcome back. So we're still thinking about this graph that was shifted right 1. But now we're going out to 3. There's 1. If I plug a 3 in there, 3 minus 1 is 2. Absolute value of 2 is 2. So we've got this little triangle and this bigger triangle. And certainly on free response, you could get away with this. Where I find that length, well, only kinda. I mean, I didn't finish that. I just said, well, that length would be this minus that. So you could leave an answer like that. I would be sad when I had to grade it, but you could leave your answer like this for free response, but not on multiple choice. On multiple choice, we're going to run into, that's 2.5, I think it is, isn't it? Because that's 1 times 1 times 1/2. And that's 2 times 2 is 4 divided by 2 is 2. So I get 2.5. 2.5. That's a 2. All right. Next. Hey, yeah, what about this one? The integral from negative 2 to 0 of x dx. Give that one a try. Okay, so we're looking at the line y equals x, but we're only looking from negative 2 to 0. We want to find this. Well, I know this length is the bigger one minus the smaller one. 0 minus minus 2. So I know this length is 2. But this, if I take this negative 2 and plug it into the function, that's negative 2. So I have a triangle. Base is 2, and height is -2. So I get the value of the integral to be -2. Now, I know you say, but Mr. Euclid, area can't be negative. And I agree. Which is why a couple videos ago I said, well, so here's the thing. We casually say area. We really mean the integral. The integral can be positive or negative. Area can only be positive. I'm appealing to the geometry of the situation by using an area formula, but if my region is below the x-axis, that integral has to be a negative number. And that's what I see here. I see my integral is -2. Yeah, I'm below the x-axis. I have to have, because of that negative height, a negative integral. Okay? So be careful about this. And it's going to come up again in chapter 7. Area would be +2, but the integral is -2. Okay, what's next? Oh, hey, what if we did this? I mean, we just saw the picture. And this is what we're trying to find. So how is this problem different from the one we just did? Any thoughts? Well, so I went from -2 to 0. I went this way. I integrated this way. And that's usually the way I do it, from smallest to largest. And remember, when we did smallest to largest, we said we would find this length by doing largest minus smallest. But now instead of doing largest minus smallest, I'm doing smallest minus largest. And so what I'm getting in this situation here, -2, 0. Now I'm saying, okay, I'm going to do -2 minus 0. And that's going to give me a length here of -2. This didn't change, right? I plug my -2 in there, I still get a -2. But look at the area now, 1/2, or look at the geometry of the situation now. Now I have a +2. Mr. Kuku, what's going on? So the direction you integrate matters. Usually we integrate this way, the direction we read in this country. Now, that is integrating this way. You know, I'm adding up slice, 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 slice. Adding up those infinite slices going this way. But here, I'm starting at 0 and going to -2. I'm going the opposite direction. And I need to be able to have that opposite show up in some way. Well, here, when this length was 2, because I was doing b minus a gave me +2. B value of 0, a value of -2, b minus a, I get a +2, so that length is 2 as I integrate this way. But if I choose to integrate in the opposite direction, b minus a turns out to be -2. And that's why that side length is -2. I'm integrating the opposite direction, adding up all these slices until I get to -2. And my integral is now positive. So we, be mindful of that. just like I need to be mindful of the fact that when my integral is below the x-axis, I expect a negative value for that integral. So too, I expect the opposite answer, depending on if I integrate from smallest to largest or from largest to smallest. Okay? In fact, we will even take this a step further with one of our integral properties. One of our integral properties is the integral from a to b of f of x dx equals negative the integral from b to a of x dx. So we can flip the bounds, but we're going to get the opposite value. And that happened for us here. When we integrated from negative 2 to 0, we had a value of negative 2. If I flip these bounds, then our answer should be negative of what we got here. Since what we got here was negative 2, and I put another negative in front of it, negative times negative is positive, this becomes positive 2. And that's exactly what I was looking at. Okay? All right. So, where are we next? How about this one? Integral from 0 to 2, negative 1 minus x dx. Give it a try. Yes, these are absolute value bars. All right, how did it go? Did you think about your graph? Did you think about shifting right 1 and flipping upside down? So there's 1, there's negative 1. We're integrating from 0 to 2. And because of symmetry, I sort of feel like this area and this area are going to be the same number. So if you want to do the integral from 0 to 1 and multiply that by 2, so you get 2 of those, that should probably work in this case. But it's really not a whole lot of work to evaluate each of these triangles. So I know that's 1. I know that's negative 1. No, it's not positive 1. Look, I have to go down to negative 1. This length is negative 1. So I'd say 1/2 1 times negative 1 for this piece, plus, what about over here? Well, here we're saying 2 minus 1 is that length, which is 1. And here, if I plug a 2 into this function, 1 minus 2 is negative 1. The absolute value of negative 1 is 1 times the negative is again negative 1. So I'm going to have 1/2 2 minus 1 times negative 1. And of course, instead of 2 minus 1, I could just write 1. And so I end up with what? That's going to be negative 1/2 plus negative 1/2 is negative 1. Okay. How about this one? The integral from negative 2 to 0 of 2x minus 1 dx. Please don't forget your dx. I'll take off a point every time you do that on a test. Those points add up fast. All right, welcome back. How'd it go? What formula did you use? What'd you see? Well, let's take a look at the graph. Up 2 over 1. So I'm looking at this. And remember, I'm integrating from negative 2 to 0. There's negative 2, there's 0. And we want this. Not that, or that. Okay, there's the point 0, negative 1. If I plug a negative 2 in here, I get negative 4 minus 1 is negative 5. So, what shape do you see? Please don't tell me you see a square and a triangle, or a rectangle and a triangle. You can. You'll get the same answer, but I really like you to see a trapezoid here. Here's the height. Here's base 1. Here's base 2. So, 1/2 the height. Well, that height is 2. How do I get 2? I'm doing 0 minus a minus 2. I'm doing the bigger number minus the smaller number. Times base 1 plus base 2. Well, base 1 is that y value, -1, and plus base 2. Base 2 is that y value. So we get that value is -6. Again, I'm happy with -6 because this shape is below the x-axis. Anytime we're below the x-axis, we really want to consider that that negative is appropriate. Our areas under the x-axis, our integrals under the x-axis should be negative. Our areas under the x-axis, they'll always be positive. But an integral under the x-axis, that's going to be negative. Okay, so try this one. We're going from -4 to 0, square root 16 minus x squared. What do you get? Come back when you're done. Well, so I was thinking this might be another one of those semicircle problems, except I noticed that we were only integrating from -4 to 0. So this part doesn't exist. Whoa. Well, that's a quarter circle. So if the area of the circle would be pi r squared, and we want a quarter of that area, this is my area formula. This is -4, this is 4. It's pretty clear to me that the radius is 4. So I'm going to have pi 4 squared over 4. This over 4, remember, represents we only want a quarter of the whole circle. And I see a quarter of the circle there, right? Yep, 1/4. So what do we get? We get 16 pi over 4, or 4 pi. This integral is 4 pi. Okay, how about this one? Integral from 2 to 5 of 3x dx. Welcome back. So if I graph the line y equals 3x from 2 to 5, I'm only looking at this. If I plug a 2 into this function, I get 6. If I plug a 5 into this function, I get 15. Now, why would I want to do that? Well, because I know the height is 5 minus 2. Base 1 is the y value here, 6. Base 2, that's this over here, that's that y value. So I do need to find these values, and I find these values by plugging these endpoints into my function 3x. So then area of a trapezoid, 1/2 3, 6 plus 15. That's 3/2 times 21. No canceling there, so 63/2. And you could say certainly 31.5 if you wanted to. I mean, on free response, you could stop here. Okay. Yeah, there's a couple more I'd like to do. How about this one? The integral from -1 to 2, absolute x over x dx. You know, we graphed this both in chapter 1 and in chapter 2. And here we are now in chapter 6, and many of you have forgotten what this looks like. A number divided by itself, most students say 1. Except, while that's true in this direction, that's why I have y equals 1 here. If I plug in a -1, -1, absolute value is 1, divided by -1 is now -1. So we're positive 1 up here, we're negative 1 down here, and we're integrating from negative 1 to 0, and we keep going until we get to 2. So what do you see? Well, I see these two regions, and I want to add their integrals up. So here, I'm integrating this way, which means this is negative 1, this is 0, and so big minus small gives me a length of 1. This is 1 times negative 1, and so we get an area, or an integral, of negative 1. And up here, well, this length is 2. This height, what's the height at 2? Absolute value of 2 over 2, that's going to be 1. And so then the area of this rectangle is going to be 2 times 1, or 2. So negative 1 plus 2 is the value of this integral, which is positive 1. Another way to understand what's going on here is this area can nibble away at this positive area, right? This negative 1 is canceled by this positive 1, leaving us the area of 1 left over. Okay. How about this one? With that last function in mind, the integral from negative 2 to 2 x over absolute x dx. Well, I hope you came up with 0 when you did that. Let's think about our graph. So this I'm looking at negative 1, positive 1. This one I'm looking at 2 times negative 1. And this one I'm looking at 2 times positive 1. Or said a different way, this amount and this amount are the same size but opposite SIGNs. So this area of negative 2 and this integral of value of negative 2 and this integral value of positive 2, when we add them together, we're going to get 0 here. Not x equals 0. That's not what that 0 represents. That 0 represents the net area here. We've got some below, we've got some above, we add them together, we get whatever we get, but in this time, we got a 0. And that means that integral is equal to 0. And I think that's a really important thing for us to recognize. We saw it a bunch. Oh no, we haven't yet seen it. Take it back. We will see a lot of times when the integral is equal to 0. And what causes the integral to be equal to 0 is that that positive area and that negative area cancel each other out. Okay. Ooh. How about this one? The integral from negative 5 to 6, 9 minus x squared over x minus 3 dx. All right. Give that one a try. So, kind of looks like a rational function. Were you scared that it'd be curvy around a vertical asymptote and you wouldn't know how to do those areas? But instead, you said 3 minus x, 3 plus x, x minus 3. Well, these are almost opposites. They would be opposites if I pulled out a negative. I'm sorry, they would be the same if I pulled out a negative. So those go. And so I end up with negative x minus 3. So I make my graph. Negative x minus 3, 3, negative 3, And we're integrating from -5 to +6. So that's -5, and that's +6. Okay, but wait a second. There's a hole at 3. Ooh, that's a hole. Does that hole... I have something wrong here. Oh, I did the wrong graph. Silly me. Sorry. -x minus 3. Okay. That's my graph. There's 6. There's -5. And we have a hole at 3. Hole at 3. So, yeah. What about that hole? Does it cause a problem for us to find the area here? 0, -3, -5. Okay. Does that hole cause a problem? And the answer is no. Remember, Euclid said a hole takes up no space. So that hole that we see there taking up space, that's not Euclid's hole. Euclid's hole is it takes up no space. So it doesn't affect our ability to integrate here when we have a hole. But I do need to know how long this is, how long this is. If I plug a -5 into this function, minus 5 is +5 minus 3, or 2. And if I do big minus small, -3 minus 5, I also get +2. So that is going to be 1/2, 2 times 2. Plus, what about over here? Well, I'm going from -3 to 6. 6 minus 3 is 9. So we know that this length is 9. And if I plug a 6 into this function, I have -6 minus 3, which is -9. So I'm going to have 1/2 9 times -9. So that's going to be -81 over 2 plus 4 over 2. Well, 87, no, 77. 77 over 2 is the value of my integral. You know, goes below, going to be negative. Goes above, going to be positive, unless we flip these boundaries, in which case instead of integrating this way, we're integrating that way. And that would then be -2. That would be a -9. Okay? But rather than do that, because that hurts my brain, even just to say those words, I always find it easier if they give me a problem like this, where I'm integrating from bigger to smaller. The first thing I do is say, no, I'm not playing that game, and pull out a negative. So we've gotten this area from this integral, and I pull out a negative, so it's negative times that integral, and that would turn it into positive 77 over 2 if I integrate it this way instead of this way. Okay. Want to do one with a radical? One with a transformation? We'll do these last two. Integral from -1 to 1 of 1 plus square root 1 minus x squared dx. That's good. You should be able to do that. All right. So were you able to see this as the semicircle shifted up 1? Okay, so semicircle shifted up 1. There's our semicircle. There's our shifted up 1. So we're looking for this area. Well, I seem to have a semicircle and a rectangle. I know that this is 1. I know that this is 1. 1 minus a minus 1 is 2. So the whole side length there is 2. This height, well, is 1. So the area of the rectangle is going to be 1 times 2 or 2. Now what about this? What about that semicircle? Well, that's half of pi r squared when the radius is 1. So we're going to do 1/2 pi 1 squared, which is pi over 2. So the value of my integral, pi over 2 plus 2. And that's it. We're all done. Yes, you could write 2 plus pi over 2, but I don't really see a difference in doing that. Okay, what was my last one? Oh, yeah, the last one. Integral from negative root 2 to 5 root 2 of r dr. Yep. Now, some people are sort of intimidated because of the negative, some because of the radical, some because I'm not using x's. Well, I trust you to know that that's the graph of y equals r. And we want to integrate from negative root 2 up to 5 root 2. So what do we have going on here? Well, it looks like two triangles. Negative plus a bigger positive. I'm expecting my integral here to be a positive number. So if I plug a negative root 2 in here, my y value is also negative root 2. If this is 5 root 2 and I plug a 5 root 2 in there, yeah, I get out a 5 root 2. So when I think about the area formula, I've got this distance is not negative root 2. This point is negative root 2. This distance is 0 minus a minus root 2 or root 2. So I've got negative root 2 here and positive root 2 here. Well, root 2 times root 2 is going to be 2. Divided by 2 is 1. Don't lose that negative. And so that's negative 1. Over here, we've got 1/2 5 root 2 times a height of 5 root 2. 5 times 5 is 25. Root 2 times root 2 is square root of 4 or 2. Ooh, 2 times 1/2, they cancel, and so all I have left with is 25. Now remember, the value of this integral is that plus that. And so we end up with 24. This matches over here, so they undo each other, and that means the area of this trapezoid is going to be 24. Okay, well, there you go. So then next semester, we're going to start thinking, hey, that's great that I can use all my geometry knowledge, but what's going to happen when I got things, I don't know how, I mean, that's not a straight line. This is no longer a triangle. So tune in January to find the continuing saga. Take care, everyone.